that classic sci-fi dream of just poof, being somewhere else entirely.
Oh, yeah. It's the ultimate shortcut, isn't it? Like
Mm.
beating space and time.
Totally. Sounds absolutely incredible.
It truly does. And today, we're diving deep into some really fascinating...
Now, when most people hear teleporter, they probably think Star Trek, scan you, break you down, rebuild you somewhere else.
Exactly. But we know that version hits some serious walls, like the no cloning theorem. Fundamentally impossible.
And this isn't the real-world quantum teleportation either, is it? The kind scientists are actually doing.
No, that's a key point. Real quantum teleportation moves information, quantum states, not actual matter, and it's still stuck at the speed of light.
So the superposition transporter, what's the big idea? How is it supposed to be different?
Well, the claim, the really big claim, is that it moves the original object, the actual thing itself.
It's the original. Okay, how?
It's proposed as a three-stage process. First, you take your object, let's say it's at location A, and you put it into a coherent quantum superposition.
Meaning
It exists somehow at both location A and a distant location B simultaneously.
wow. Okay, that's already bending my brain literally in two places at once.
That's the concept, yeah.
Yeah.
It definitely challenges our everyday intuition. So stage 2, you manipulate its wave function.
The wave function, that's the quantum description of this two-place state.
Exactly. You'd use like external fields to deterministically guide it. The idea is to basically dial down the probability of it being at A and crank up the probability of it being at B.
To sort of push the odds toward the destination.
You got it. And then the final stage, force the wave function to collapse
Collapse how?
so that the object is definitely at location B, fully materialized there.
Okay, on paper, that sounds almost elegant. A three-step quantum move.
It does have a certain logic to it, but, and this is the core of our deep dive today, based on these sources, this isn't just an engineering challenge.
Here it comes.
Yeah. It faces, well, a whole cascade of really profound, fundamental physical impossibilities. Things that seem to make it genuinely unattainable according to the laws of physics as we understand them.
So we're not just talking, we need better tech. We're talking, the universe says no.
Pretty much. We're looking at fundamental no-go theorems baked into quantum mechanics itself.
Okay, well, I'm ready. Let's walk through these barriers. I have a feeling we're going to hit some surprising stuff about, reality and what it even means to be somewhere.
Exactly. Get ready for some aha moments,
Ah.
definitely. This really challenges how we think.
All right, so if you want to transport something this way, where does quantum mechanics throw up the first major roadblock? Step 1, I guess.
You're right. It starts right at the beginning. Defining the object you even want to transport.
Defining it.
Yeah, the transporter, as proposed, needs a complete quantum mechanical description of the thing, the whole macroscopic object. And this immediately crashes into what we can call an insurmountable informational barrier.
An informational barrier, meaning?
Meaning it's rooted in like 3 absolutely fundamental principles of modern physics. It's not just hard to know, it might be impossible to know.
Okay, so hurdle number 1 is just knowing what you're trying to move.
Yeah.
It sounds like you're saying it's not just difficult to measure, you fundamentally can't know its exact state.
That's precisely the issue. In quantum mechanics, right, any isolated system is described by its wave function. That's the math thingy that holds all the possible information about it.
Okay.
Now, for something big like a person, you're talking roughly 10 to the power of 27 atoms. That's not just 1,027 separate wave functions. It's one single, unified, unbelievably complex universal wave function for the whole system.
One function for everything, every atom.
Everything.
Yeah.
And it exists in this abstract, high-dimensional space. It's not just mapping where each particle is, but all the possible configurations of all those particles all at once, plus things like spin.
That sounds vast.
Staggeringly vast. It describes this incredibly intricate web of correlations, quantum entanglements between every single particle. This is the complete blueprint the transporter would need to grab and manipulate.
And you're saying this blueprint, we can't actually read it. It's fundamentally unknowable.
Pretty much, yeah.
Yeah.
Because of Heisenberg's uncertainty principle.
Okay. I know that one. Can't know position and momentum at the same time, right?
Exactly. And it's not just about our clumsy measuring tools. It's built into reality. To define that initial wave function perfectly, you'd need the exact position and the exact momentum of every single one of those 127 particles. But Heisenberg says, nope. Measure one precisely, you fuzz out the other.
So the starting conditions you need, you literally can't know them.
You literally cannot know them. Any attempt to measure creates uncertainty.
It's like trying to grab smoke. The act of grabbing disperses it.
That's a great analogy. And then there's the sheer amount of information itself. Even if you could know it, there's the Bekenstein bound.
Bekenstein bound, that sounds familiar. Black holes.
Exactly. It comes from black hole thermodynamics. It basically sets an upper limit on how much information you can cram into a finite region of space with a finite amount of energy.
And a person's quantum state would be?
Astronomical. The Bekenstein bound suggests the information needed for a full quantum description of a person could rival the information content of a black hole of the same mass. It's an unimaginable quantity of data.
Wow.
And it's data that the uncertainty principle already tells us we can't fully access anyway. So Bekenstein quantifies the scale of the information that Heisenberg says is unknowable.
Okay, so Heisenberg says you can't know it precisely. Bekenstein says even if you could, it's an insane amount of information. What's the third part of this information problem?
That's the no cloning theorem.
Ah, the reason Star Trek doesn't work.
Precisely. Even if, let's say, you magically knew the complete quantum state, the theorem says you cannot create an independent, identical copy of an unknown quantum state.
Why not?
Because to copy it, you'd have to measure it, right?
Mm-hmm.
But measuring a quantum state collapses its wave function. You destroy the very state you were trying to copy in the process of looking at it.
So no backups, no test runs, no way to check if you got the state right before you hit go.
None. Any measurement to verify the state would be an observation, collapse the wave function, and the whole transport attempt fails right there. That's work directly and kind of blindly on the one and only original unknown quantum state.
Okay, so those three together, uncertainty principle, Bekenstein bound, no cloning theorem, they sound like a complete trap.
It's like a logical trilemma, yeah. The transporter needs the state information, but the state is fundamentally unknowable, unverifiable, and uncopyable. It's a paradox right at the foundation.
All right, that's a big hurdle. But let's play devil's advocate. Let's imagine, somehow, we wave a magic wand and get past the information problem. What's next? Putting a whole person into this quantum superposition state.
Right. Stage one of the actual process.
We see, single electrons being in two places, but a person, a whole macroscopic object, that just feels wrong.
And that feeling points to arguably the most physically formidable obstacle. Quantum decoherence.
Decoherence, okay.
So yeah, quantum superposition works beautifully for single particles, tiny systems, but scaling it up so that the entire center of mass of a 27 particle object is in two distinct, far apart locations simultaneously. That's a completely different ballgame.
It would mean all those particles' wave functions have to be perfectly linked up, perfectly coherent across both locations.
Exactly. Coherently delocalized and entangled in this extraordinarily precise way.
But wait, what about things like superconductors? Or those Bose-Einstein condensates? Don't they show quantum effects on a big scale?
They do. And they're amazing. They show a collective quantum behavior in billions of particles. But it's usually superpositions of internal states, things like momentum or spin. It's not typically a superposition of the entire object being in two completely separate places as a coherent whole. That's the key difference.
Okay. So the reason my coffee cup isn't also currently in the fridge is decoherence. How does that actually stop it?
Precisely. That superposition state, that delicate being in two places at once state, is unbelievably fragile. Any interaction at all, between that quantum system and its external environment acts like a measurement.
A measurement, even if nothing's deliberately looking?
Yep. The interaction instantly entangles the system with the environment. Think of it like information about the system's state leaking out. This destroys the crucial phase relationship between the two parts of the superposition.
And poof.
Poof. From the system's point of view, it looks like a super fast, irreversible collapse into just one definite classical state. It's forced to choose a location.
And for something as big as a person, what counts as the environment? What kind of interaction are we talking about?
Oh, pretty much everything imaginable. Tiny things. Thermal photons, heat radiation coming off the object itself. If even one photon scatters off it and flies away, it carries information about where the object was. Collapse.
Just one photon.
Just one. Or think about air molecules bouncing off it. Stray cosmic rays zipping through from space. Even neutrinos, which barely interact with anything. Any interaction that depends even slightly on the object's location will leak that information.
You're not going to say gravity too, are you?
Absolutely.
Nice.
Gravity too. The object's own gravitational field would also have to be in a superposition, right? affecting space-time differently around location A and location B.
Okay, that's wild.
That superposed gravity field would interact differently with Earth's gravity, the sun's gravity. If even one hypothetical graviton, the quantum particle of gravity, gets emitted or interacts, it leaks location information. Collapse.
So the universe itself is constantly measuring everything.
In effect, yes. The decoherence timescale, the time it takes for this collapse to happen for a macroscopic object, is just unfathomably short. Way, way faster than any time you'd need to actually manipulate or transport it. The environment pins it down to one reality.
So to make this superposition transporter work, you'd need perfect vacuum, absolute zero temperature, complete shielding from every photon, particle, maybe even gravity.
You'd need an impossible level of isolation, something far beyond anything found naturally or likely achievable.
And wouldn't the transporter device itself cause problems? The machine holding you in the superposition.
You've hit on a huge paradox.
Yes.
The very apparatus you'd need, the lasers, the magnetic fields, the physical container to create and control this state, is part of the environment. It has to interact with the object to control it. So maintaining the quantum state needs perfect isolation, but controlling the state requires interaction. And the stronger the control you need for a massive object, the stronger the interaction, and therefore the faster the decoherence.
It's a catch-22. Controlling it destroys it.
Fundamentally, yes. The control mechanism is inherently at odds with preserving the superposition.
Okay, this decoherence barrier sounds immense. What's, like, the biggest thing we have managed to put into a superposition of places? Is it even visible?
Well, the current record holder, I believe, is a tiny sapphire crystal. About 16 micrograms. You could barely see it.
16 micrograms. That's nothing compared to a person.
Trillions and trillions of times less massive. And critically, it wasn't a superposition of being in two different rooms. It was a superposition of two slightly different vibration states. The actual spatial separation involved was minuscule, far smaller than an atom's nucleus.
Wow. Okay, so even getting a tiny thing to vibrate in two ways at once is incredibly hard.
Exactly. These experiments are amazing science, but they really highlight how dominant decoherence is for anything remotely large.
All right, let's keep waving the magic wand. Let's say, hypothetically, we solve the information problem and the decoherence problem. We have our person in a stable superposition across two locations.
Okay, a very big if, but let's go with it.
Stage 2 was manipulating the wave function, right? Shifting the probability from A to B. This involves the Schrödinger equation, doesn't it?
It does. The time evolution of any isolated quantum system, how its wave function changes over time, is governed by the time-dependent Schrödinger equation.
And that equation is deterministic.
Yes, it is.
Yes.
If the system is truly isolated, the equation describes a smooth, predictable, reversible evolution of the quantum state. No information loss, no randomness. If you know the starting state and you know the Hamiltonian...
The Hamiltonian, that's like the energy and forces acting on it, the control knob.
Exactly. It represents the total energy and encodes all the interactions. If you know the initial state and you can control the Hamiltonian perfectly, you can, in principle, steer the wave function precisely where you want it to go. Apply the right fields, guide the system from state A to state B. That's the core idea of quantum control.
So the plan would be, apply one field to create the A plus B superposition, then apply another really complicated field to smoothly shift all the probability amplitude over to B, making the chance of finding it at A effectively zero.
That's the theoretical plan, yeah.
Sounds neat. So what's the catch this time, assuming we can keep decoherence away?
The catch is twofold: computational complexity and energy cost. Both are astronomical.
Computational complexity for what?
For calculating the exact Hamiltonians, the precise control fields needed to guide the wave function of maybe 127 entangled particles.
Yeah.
The complexity of that calculation grows exponentially with the number of particles.
Exponentially.
Yeah. It's the same reason even our best supercomputers can't perfectly simulate moderately complex quantum systems, like large molecules.
Wow.
Scaling that calculation up to a human being isn't just a matter of waiting for faster computers next year. It's a fundamental exponential barrier. It might require more computing power than exists in the universe.
Wait, so the computer needed to figure out how to build the transporter, would have to be powerful enough to simulate the person quantum mechanically anyway.
That's a really interesting point, actually. Yes, the computational problem of designing the control fields is basically equivalent in difficulty to just simulating the entire quantum system. If you had a computer powerful enough to design the transporter,
you could already manipulate a perfect simulation of the person. What would be the point of the physical transporter then?
Exactly. It's another kind of paradox. The technology needed to design the device is functionally the same as, or even more powerful than, the device itself.
Huh. Okay. And the energy cost? I'm guessing it's not low.
Not even close. Think about generating and rapidly changing the incredibly powerful and complex electromagnetic or other fields needed to control the collective state of 10,000 to 27 particles across potentially large distances.
You'd have to control the energy landscape everywhere the object is and in between.
Pretty much. The energy needed for that kind of macroscopic, high-speed quantum manipulation would likely be, well, let's just say it would dwarf the output of entire nations, maybe civilizations. Astronomical is the right word.
Okay. Information barrier, decoherence barrier, control barrier. We're running out of stages. Stage 3 was collapsing the wave function at location B, making sure it arrives.
Right. The final step. And this is where we slam headfirst into the measurement problem, possibly the deepest, most argued-over mystery in all of physics.
The measurement problem, because the transporter needs a guaranteed arrival, right? Not just a probably arrive.
Exactly. And the idea of forcing a collapse to the outcome you want, well, it misunderstands what measurement means in quantum mechanics, at least in the standard view.
Which is the Copenhagen interpretation.
Yes, the standard Copenhagen interpretation. In that view, wave function collapse is this abrupt, discontinuous, probabilistic thing that happens when a measurement is made. The Born rule gives you the probabilities.
So even if you did everything right in stage 2, manipulated the wave function, so it's like 99.99999% likely to be at location B.
There's still that tiny, tiny non-zero chance it collapses back at location A instead, or somewhere else entirely, depending on the setup.
Which, for a transportation system, is catastrophic failure. You can't have a 1 in a billion chance, you just don't arrive, or reappear where you started.
Precisely. Quantum mechanics, under Copenhagen, simply doesn't allow for guaranteed outcomes in measurements. It gives you probabilities.
Yeah.
The theory doesn't even provide a mechanism for the collapse, it's just postulated. So you can manipulate the odds before the measurement, but that final roll of the dice by nature, it's fundamentally random and beyond your control. Forcing a definite outcome just isn't in the rules.
Okay, but what about other interpretations? Are there quantum interpretations where this might work? Ones without random collapse?
People often ask that.
Hmm.
Unfortunately, the alternatives don't really help the transporter case either. Take the many worlds interpretation, MWI.
Right, the one with branching universes.
Yeah. MWI gets rid of collapse altogether. It says, when a measurement could happen, the whole universe splits. Every possible outcome happens, but in a different parallel branch, a different world.
So, if our transporter operates under many worlds, what happens?
When the arrival measurement happens, the universe splits. In some branches, you successfully arrive at location B. In other branches, you're still back at location A, or maybe splattered somewhere in between in others.
That's not transport, that's just making copies of the universe where maybe one version of me gets there.
Exactly. It's a universe duplicator, not a transporter. It fails the basic requirement of reliably getting you from A to B in this reality.
Okay, so MWI is out. Any others?
Well, you have things like objective collapse theories, which try to build collapse into the physics as a real, spontaneous process, but those are also typically random. Then there's Bohmian mechanics, where particles always have definite positions, guided by a wave function. But in that view, the whole idea of a macroscopic object being truly in superposition at two locations doesn't really make sense in the first place.
So basically, no major interpretation of quantum mechanics gives you a way to guarantee the arrival.
That's right. The transporter's core function relies on solving the measurement problem in a way that allows controlled, deterministic outcomes. And that's one of the biggest unsolved puzzles in fundamental physics.
Wow. Okay, so yeah, this isn't just hard. This sounds genuinely impossible based on the physics we know.
That seems to be the consensus from the sources, yes. Fundamentally impossible.
But you know, even though it's impossible, thinking about why it's impossible has been incredibly illuminating. It really forces you to grapple with what quantum mechanics actually means.
Absolutely. That's the real value here. The superposition transporter, even as a failed idea, is a fantastic pedagogical tool, a philosophical tool even.
Yeah.
Yeah, because analyzing why it fails forces us to confront these deep quantum mysteries. What is the wave function, really? How does our solid classical world emerge from this weird quantum fuzziness?
Yeah.
And as we just saw, what on earth is going on with measurement?
Okay, so let's quickly recap those huge barriers we walked through. The 4 big no-go signs for the superposition transporter. First,
the information barrier. You fundamentally can't know, measure, or copy the complete quantum state of a macroscopic object. Heisenberg uncertainty, Beginstein bound, no cloning theorem. Game over before you start, really.
Right. Second.
The decoherence barrier. Macroscopic superpositions are ludicrously fragile. The universe is constantly measuring things, destroying quantum coherence instantly. An object like a person simply cannot exist in two separate places in any stable way.
Got it. Third.
The control barrier. The mind-boggling computational difficulty of figuring out the control fields, the astronomical energy costs, and that paradox that controlling the state destroys it through decoherence anyway.
A triple whammy there. And finally, fourth.
The collapse barrier.
Yeah.
The measurement problem. You can't force a specific outcome from probabilistic quantum collapse in the standard view. And interpretations like many worlds just create parallel universes, which isn't transport.
Okay. And these aren't just, problems waiting for a clever engineer. You're saying they're baked into the fundamental rules of the game.
They seem to be, yes,
Hmm.
rooted in the foundational laws of physics that describe how our universe operates.
But, okay, let's end with a bit of that philosophical angle you mentioned. Here's a thought.
Yeah.
If, and it's a massive if such a transporter were somehow possible,
Okay.
and you went through it, and the person who arrived at location B felt like you, had your memories, your consciousness, maintained that sense of self, what would that tell us about what you actually are?
Ah, that's a profound question. If your continuous stream of consciousness, your identity, could survive that kind of discontinuous jump where your original atoms cease to exist here and reappear there,
Yeah.
what would it imply?
Yeah.
Well, it could be seen as the ultimate validation of physicalism, right?
Sure.
The idea that mind, consciousness, identity, it's all an emergent property arising purely from the physical seat of your brain matter.
Yeah.
If preserving the complete quantum state perfectly preserves you,
Then maybe you really are just the information encoded in that state.
that's one way to look at it. The pattern, the information, is the person.
But what if you didn't survive? What if the process worked, a physically identical copy appeared at B, but your subjective experience ended at A? The lights just went out for you.
Then that would strongly suggest there's something more to identity than just the physical arrangement of atoms. Something non-physical, maybe. An immaterial soul or some essence of you-ness that isn't captured even by the complete quantum state.
So this impossible machine forces us to ask, is the quantum state of our atoms all that we are?
It's a question right at the boundary of physics and philosophy, and honestly, it highlights how much we still don't understand about consciousness itself.
Absolutely. Definitely something for you, our listener, to ponder. Keep exploring these connections between physics, philosophy, what it means to be you. This deep dive is really just scratching the surface. Thanks for joining us.